So reinforcement learning does not need from you any training data. It just needs some set of rules, and it just needs the goal that you want to set, and it dynamically creates training data as it trains itself. So one classic example is this AlphaFold that got the chemistry Nobel Prize this year. It's a reinforcement learning algorithm. Okay, and then in chess, the same company has called Alpha Zero. Or you will need to give to Alpha Zero is the rules of chess, and not all the chess games or grandmasters have played. No, just the rules. And then you tell that the your goal is to win. So it plays with itself, the algorithm. In this way, it dynamically creates the chess board positions, right? That is its data, and then it learns how to act in a given dynamical speculator. What is the best way to attack? In this way, it teaches itself chess, and it took like only 4 hours to surpass the human level. So these are very powerful machine learning algorithms. Now that marks the end of this intro. Now we will go a bit deeper. Some concepts in machine learning. Okay. So train test split, as I have mentioned it. Normally, when you have some data, you split it into train and test set. Why? Because you want to evaluate how the model performs on unseen data. So you take out some of the data as unseen. So you do not train on this part. You keep it separate for testing after you think that you have trained the model. So, and as I said, that the success or the performance of a machine learning algorithm is measured by unseen data set and not by the seen data set. And this is called the generalizability. Normally, we make a 80-20 stick, so we take 80% of the data set as training and 20% for testing. Now, a question to you: why do we do it like that? Why 80-20? Why not 50-50 or 20-80? So this is a question to the audience. Yes. You can speak up or you use a microphone. Hmm? Uh,
So we take the train data set from the test data set from the train because we need to cross validate between the biggest. So let's say I have 100 data points and I have taken 80 out of them and tested the 20 data points. Then again, in a different situation, I can take another 80 training points and test on another 20 data points. So we can uniformly test on all the data points and it will make the trading model more accurate.
you went, what you said is correct, but you went beyond what I was talking about. It's the next step. My question was even simpler. Why the split is 80-20 and not 50-50 or 20-80?
Because you had no distance. Um,
Because as you have seen, you expect the algorithm to learn more with more data. So you do not want to throw away your data set, right? So as if you want to use 100% of your data to train, but you cannot because we need some unseen set to test. But the question is why is not then 99 and 1? Not really. So why we don't take say 99 and 1? Not quite. So the answer is light in sampling bias. So when you have a test set and if the test set is not sufficiently large, it could be just a proof that you get some good test performance. Whereas the test set should also be large enough so that you can consider it as a true representative of the population, right? If you just have a small test set, say 1 point, and you are like, oh, you say, wow, my model performance is 100%, or you see your model fades. So most samples cannot be trusted, right? The uncertainty is huge. So you do not want to make the training set very small. So we find a balance in between, like 80-20. Then what's your name? What she has said is something goes beyond that. Then this 80-20 split you you can do across the set, you have across the 100% to do something called cross validation. But I'm not going there. Okay? So think about this problem on x-axis. So we take a very simple problem. The sunshine of hours. So probably this does not apply so much in Bangladesh, but I live in Germany, and in Germany it applies a lot. Sunshine of hours, hours of sunshine on a day, and ice cream consumption per kilogram per person. So the plots they look like this. Okay, so now comes one thing I forgot to tell you there, that in the slide before you saw that when we talked about the train test split, we labeled that train data set with orange. Do you see this color as orange or red? Orange, and the test set is black. Okay. So let's take the training data set and let's be very naive and let's make the simplest possible model, then a straight line. Okay. So you have this sunshine, hours of sunshine and ice cream consumption, and you said that you want to make it model like this. Whereas you might think that the best model could be a curve like that. Probably. Or you can go to other extreme, right? And think of a very complex model that passes through each point. So I remember when we were in undergrad first year, we had to make plots of in physics experiment, and everybody tried to make this plot both to all points. One, is it not good? Do you know? This is a too complex model, and you are going to see why it's not good. So you have these two extreme cases. Question is which one is good, right? Now there is something called either residual for error, right? If this green line is your simple model, and if this green curve is your complex model, you can compute the error that the model made on training insect, right? You see that the simple model made a lot of error for the training set, but the complex model made zero error for the training set. So is this good? It made zero error, right? Is this good? Yes or no? Because as I said, the performance is measured with the unseen data. You need to see if it performs well for the black dots, not the red ones. And quite unsurprisingly, you see that they both fail. Maybe the more complex one perform worse, right? So complex things are not always good. So what we sort of see from here, we need to find a balance between simple and complex, right? So let's talk about some machine learning terminology. When you have a very simple model, we say that it underfits the train data. Because to draw a line, how many parameters do you need? Two, right? So it has learned only two parameters out of this data set. So it has not learned much, right? Only two. So maybe it could have learned more to have a more complex shape, but we did not let it happen. This was a choice that we are trying to write a straight line. Okay, so in this case, we say that the model underfits the training data. It could have fitted more, and we say that this is high bias. What does it mean by bias? It has high bias as it had not made a lot of error. Okay, this is what bias means. We're gonna talk more about bias and variance. This is the part, and we will say in this case this is low bias on the training set. Bias basically computes that intrinsic error it made. In this case, it has not made much. Okay, but then when it comes to the test set, you see that the simple model has low variance, and the complex model has high variance. What does it mean by variance? Where you take different training sets, as Shia pointed out, that we could make this 80-20 split across this 100%. So we could have we could have had five train test sets, five on them. So in every case, your training set is different. Now you do not expect to get the same model in despite different cases, right? Because your training set is different and your model parameters are getting learned from the training set. And the training sets are different. So this variance computes the variability of your model on the training set. If it changes much from training set to training set, this is not good, because you want your model to be insensitive to change in the training set. There's a quality of a good model, right? It should not vary much. So the problem with too complex model that it learns too much from the data. It also learns the noise in your data. You have always noises, as we'll see, and you do not want to learn the noises because those noises are useless information. The problem with complex model is that you consider the noise as also part of the true data, and then it learns the noise, and because of this is it varies too much based on training set 1, training set 2, so on so forth. Whereas the simple model does not learn much, so it does not care much of the training set, and it does not vary much based on the change in the training set. That's why it has low variance, and we'll see why these things are important. But in both cases, we see that it does not perform so well on new data, right? So now comes one of the most important slides. Let me move these things up. So This is a mathematical theorem. I know many of you are here from math and from computer science. So I don't want to prove this, but this is a theorem based on the definition of bias, variance, and noise, and based on the definition of generalization error. You can prove this theorem. Okay, generalization error has three distinct parts: bias, variance, and noise. And once again, generalization error is the error you make for unseen data. Okay. So what is variance? Variance, as I said, is how much the model varies if trained on different training sets. Okay. It computes the model sensitivity on the change of training set. Bias is the model's inherent error even with infinitely large training set. So why you have variance is that you cannot deal with infinitely huge training set, right? You real life we always work with sample. If you want to test the efficacy of COVID vaccine to humans, you cannot possibly consider all humans that live on this planet and all humans that will live in all future, the errant live all past. It's impossible to make your training set infinitely large. That's why we do have variance, but you want to minimize it, right? On the other hand, even if you have an infinitely large training set, you will always have some error because your model can never be perfect. Okay, so this is bias. So these variance and bias are related to your model and algorithm, but then something is something that bot says us that I had this thing in my hand. It is a noise that is the characteristic of your data set. Think about the situation that you go to a shop near Nika and you want to buy a piece of cloth, right? It's not a fixed price place, right? The same shirt will sell many different prices, right? So you have the same shirt, and if you take all these features of the shirt, type of fabric and size and all these things, male versus female, so on and so forth, and then you have the price. The same shirt can have five different prices, right? And this is the concept of noise. So even if your independent variables are the same, your target variable has five different values. So which one is right? None of them are right. So you can take its mean and deal with the mean, but the rest is noise. Right? In real life, we have a lot of noise. It is often intrinsic in the system. Sometimes we cannot measure well because of this. We have measurement errors, and so many factors are there that most of the real life data is noise, and this noise is the inherent uncertainty in data distribution at teacher representation. This noise is the minimum of the generalization error for the most ideal model. For the perfect model with noisy data, you can have zero bias and zero variance, but there will be noise. But we never will have zero bias and zero variance for realistic problem. Okay, so keep this in mind. So the goal is to have minimum bias and minimum variance, right? Then you have some hope to have a good model. But then, as a function of model complexity, the curves look like this. The bias actually goes down with model complexity, where the variance goes up with the model complexity. Think about complexity as the number of model parameters. The more the model parameters are in number, the more complex the model is. And that, as I have tried to show you before, so there is a trade off like this. If you make it too complex, you get a high variance. If you make it too simple, you get a high bias. So you need to find a model in between. You need to find a sweet spot where the model is just as complex or just as simple. Okay, and there is this point where you have minimized the generalization error. So when the model has high variance and low bias, you call it overfitting. Okay, and that case is underfitting. So to come back to the question of why, when you plot a graph, why don't you make your graph go to all points? Is that at these points where you measure them in laboratory, you have measurement errors? It has a lot of noise, and by making it like this, you are also including noise in your model, which is not good. This will be overthinking. Yeah. Any questions up to now? If not, we're going to the next topic. Optimization algorithms. So let us make a quick recap of linear regression. In this talk, since it's meant to be high level, I am going to write down for you a very simple model, just a linear regression. Okay, but of course, whatever I'm telling you here applies to more complex models like deep neural networks and all that. So suppose you have a bunch of independent variables x. Okay, say you have said j of them, x1, x2, x3 up to xj, j of them, and then you have some observation with x and y, different x's and y. You have say n of them, n observations and m teachers or x's. So you might want to make a model of this sort. It's called a linear regression model. Now, question to you: why is this called a linear regression? Anyone know? Why? So that the reason why this is called a regression is just the fact that the target variable in this case is a continuous variable. But why is this linear? Any you do you say that this right hand side is a line? That's why. But what if I see that some x's divide with y more or less like x squared? So what if I take here higher powers of x? Will that still be a linear expression? Yes, that is not correct. Linear regression is just a name. It can contain non-linear terms. The the linearity comes in the coefficients, because the model is learning not x. The model is learning the b. As long as the coefficient b are not appearing with higher power, it's a linear model, and this will be clear too. So a linear model does not need to be as naive as you think. It can contain logarithms, sines, cosines, powers. Only have to make sure that you do not have linearly dependent variables. But log of x, sine of x, or x squared is not a linear function of x, right? Then it's okay. You can, but the point is that these B's do not have higher powers. You don't have B1 squared or things like that. And why are you will see soon. But okay, say in shorthand we can write it like this in make matrix form. Okay. Now out of this model, the model prediction we write as y hat. But then y hat does not need to be the same as y. Y is the label, and there comes the noise, right? Error or residual. This is the model prediction. This is the ground truth, and they are not the same. And as some of you has pointed out, what could be a performance metric for a regression task? It could be the mean squared errors of this sort. And when we use a metric like this, it's called ordinary least squared. And some of you might have done it in your undergrad physics lab. The the thing is that for this problem, we don't need to use any machine learning. We can simply solve it, right? In this form, right? Correct? And this is called the normal equation. But you see that you cannot invert this x transpose x e if when we cannot we when we cannot invert in matrix. Well, say the x's are linearly dependent, right? So you make sure that there are no features for x that are linear combination of others. Then this is gonna pay, right? So, but as you see that the whole point is that you are solving for b. So all you care is whether the system of equations is linear in b or not. That's why linearity in the model parameters is the point, and that's why it's called linear regression. You don't care of non-linear functions of x. That's okay. Now the problem with this normal equation, although it's a closed form solution, that it is computationally very, very expensive. And when you have huge data set to learn, you cannot really do much with this. Okay. And therein comes what is one of the main things I'm gonna convey to you is the gradient descent. And this is also called the method of thickest descent. This was given by Cauchy in 1847. It's an iterative optimization algorithm to find the minimum of a function. And since our performance metric it is say the mean squared error, we want to minimize it. And we want to find the minimum of this function, and this gradient descent will help us. It's a good alternative for finding optimal parameters b0, b1, b2, so on and so forth. The best values of them. This is a closed form solution, the normal equation, but this will not be a closed form solution because this is a numerical approach. We start with a random guess for the model parameters b0, b1 and so forth, and we perform minimization steps until optimal values are reached. Okay. So think of this thing, this j of b, we call it a cost function. Okay. And we take a factor half. This is just a convention. Take this mean squared error multiplied by half as your cost function. And it is clear here, no, that the cost function is a function of the parameters and not the function of x and y, because you have sum over x and y. Okay. So the only way the cost function changes when you change your model. you take a different set of B, B0, B1, so on and so forth, you come up with a different cost function. And it shows here it's a function of the B's. We can iteratively update the parameters B by computing cost function at every step. Okay, we want to minimize the cost function here, right? The model learns from training data over time, ultimately minimizing the cost function. But how does it do it? Okay, we find the model parameters by gradually minimizing the cost function. We go downhill in the direction of the steepest slope. The endpoint is dependent often on the initial starting point. It's like climbing down a hill to a valley, and that's why it's called a descent. But this will be clear to you in a second. So think of a very simple cartoon scenario where you look at one parameter B, and here you plot the cost function. You see that the LSC is the equation of a parabola, right? So it's convex, and there is a single global minima. Okay, we want the minima of this cost function. We can start with some random value of B and keep changing the B until we get the minimum. And how do we update them? I'm going there in a second, but first I tell you when this is useful. This optimization procedure works well for linear regression, as you see. And when you use this sort of linear and algorithm to for a classification task, it's called a logistic regression. And then there is some more complicated version of linear regression. It's called support vector machine. For this kind of linear algorithm, this is used. More importantly, this is also used in deep neural network where you have this deep learning chat GPT. All these things they use gradient descent. But since they are very complex models, they use something else on top of gradient descent. This is called back propagation. And I'm not sure if I will have time to talk about it, but I will probably say a few words. So deep learning uses gradient descent plus back propagation, and the guy who got Nobel Prize this year, Geoffrey Hinton, is one of the founding fathers of this back propagation technique. So this is computationally simpler as I mentioned to you earlier. Now, the most important thing is how do you update the parameter, right? Suppose you start with a random set of the parameters B0, B1, so on, so forth, right? Then what you can do, as you are seeing that the cost function is simply a function of the parameters, you can take derivative with respect to the parameter. So if this number is negative, what does it mean? It means when you increase B, the cost function is going down, right? And you want to minimize the cost function. So if B goes up and the cost function goes down, this thing is negative. And then there is a minus sign, minus makes it plus, and then it alpha, which is called a learning rate, is positive. Then this whole thing is positive, right? So it means that if you increase B and the cost function goes down, you update the B in such a way that the value of B is increased. Likewise, if this sign is positive, you want to decrease the value of B, and then the update equation works. It's very simple, right? So this alpha is called the learning rate. It is also called the step size, is the size of the steps that are taken to reach the minimum. So let me take let me say a few words here. So how this thing is different in deep neural network. Deep neural network is very complex. It has many units of computation, and each unit has its own weights and biases like this piece and bunch. So when you compute the cost function, you need to send your signal back to every units individually. Then how you should update your weights and bias. In this case, you need to compute the gradient, but that then since these gradients are connected to each other, you need to use the chain rule. Multiply functions, unity is functions of functions of functions. It's a very complex function, so you need to use the Leibniz rule, chain rule to multiply many different derivatives to update these weights and biases, and that is called back propagation. That is the main thing that makes the deep neural network works. Okay, it's just a more sophisticated version of this. So to sum up, you define a model, you define your cost function, you choose some random values for your model parameters, and you start to climb down the hill, take derivative with respect to your parameters and set your learning rate, adjust your parameters, repeat until you cannot improve more, right? This is the algorithm. Learning rate is, I mentioned to you, it's a positive number, and learning rate is very important to find a good value of learning rate. It cannot be too small or too large, because if it's too small, will take forever to reach the minimum. And if the learning rate is too large, what will happen? It will make big steps, and this will jump across the minimum, and will never reach it. And this problem is called overshooting problem. So it has to be carefully chosen. So you see this cartoon here where the learning rate is too large, it just bounces back and forth, and it does not go here. In the learning rate is too small, it's taking forever to climb down. So you need to choose some sweet suitable number, not too small, not too large. The main challenges of gradient descent. You see, here I wrote down for you a very nice function, the mean squared error as a cost function is a convex function, namely has a single global minimum. So no matter where you start, you will always reach the minimum. But that's not always the case. In particular, if you had a very complex cost function which is not convex, you can have local minima, and you can also have saddle points, right? So in particular, as non-convex problems emerge, gradient descent can struggle to find the global minima. Then there is also challenge when you have unscaled data. Without scaling, the gradient descent algorithm needs more time to find the minimum. So what does it mean? The second point. Suppose you want to predict the ice cream sale, right? There we wrote down just one independent variable, the amount of sunshine. So amount of sunshine in hours can be 5, 6, 7, 8, 9, 10, 12. But then you could also consider some other variable like humidity, right? Humidity you could choose in percent, right? So when you choose humidity in percent, what are the values it takes? The values are 80, 90, 30, 50, right? Whereas the hours of sunshine has like around 10. So there is an order of magnitude change in these two different variables, right? And that is not good because then the machine learning algorithm will not treat each of them the same way. So you do not want to give unnecessary importance to some X compared to such some other. So we need to scale them the same way so that they have similar values. And this really helps the gradient descent to be faster, right? If you are using different units, it's like in the climbing down in the parameter space. If you are driving here in data, and I tell you that when you go to the left and right, you need to use feet as your distance. And when you go forward backwards, you need to use kilometers as your unit. It's very inconvenient, right? To navigate that. So when the units are very different, the gradient descent algorithm does not perform well. So you might have to take care of this to scale the data the same way. Okay, similar numerical values. Then last but not the least, you could have the vanishing and exploding gradient problem. When some gradients are zero, you do not move, or when some gradients are infinite, your algorithm becomes unstable. But there are solutions to them which I don't have time to talk about. Here I just will finish with some variants of gradient descent. By the way, how much time I have? Oh, we're supposed to finish soon, right? Yeah. Yeah, okay, good. So you see, there is this cartoon of great gradient descent. Yeah, climbing down valley. So one is called batch gradient descent. When you use on your data set to update your model parameters, that's called batch gradient descent. But algorithm is faster than normal equation, but it is still very slow and computationally expensive if you have a lot of data. So and sometimes your RAM might not be able to deal with that. So what is the solution? One solution is to use stochastic gradient descent. What you do? You take one sample point and then you compute the gradient based on that. Then climbing down will not be so smooth. It will be zigzag, and it's like a stochastic process, like the walk of a drunk person moving back and forth, but finally it goes to it. So it's much faster because you deal with just one single data point per iteration. And the most important thing is that if you have a local minimum, when you use stochastic gradient descent, you have the chance to jump out of it. if you are using batch gradient descent, you can never come out of local minimums. Yes, it's a stochastic process. It can jump out of local minimum. So if you think that your problem is non-convex, it might have some local minimum. Maybe you can take this approach. And in this stochastic gradient descent, you might be very close to the global global minimum, but you will never reach it actually. Then we have something in between, which is the mini batch gradient descent, which is you take chunk or subset of your data to train, right? That is something in between. This is mini batch gradient descent, and in deep learning, normally you we deal with huge models with huge amount of data. Normally in deep learning, what we do is the mini batch gradient descent, say of size 32, 64 sample points or 128. These are the normal sizes. So it performs faster than batch gradient descent, slower than stochastic gradient descent, but the final results are better. So I don't really want to talk about this back propagation algorithm. Just a few words. That artificial neural networks are the underlying units of deep learning, and they're inspired by the human brain neurons. How they work, the neurons are dendrites that collect signals from other neurons, and then here is the cell body that computes it. And then this computation is sent through this action, and then the action terminal will have or not have some signal passing to the next neuron based on some pressure. So just from this idea, you can have some system where some units come in, some signals, and then you make a computation, and then you pass a signal. This is called a artificial neuron. But then you can have many of them in many layers. Then you have an artificial neural network. Each of them are, you see that when I say here you have different inputs, right? And these different inputs get com- computed here. What we mean by that is that you take linear combinations of the inputs, and then here you use some sort of non-linear function to say whether certain input will give you a 0 or a 1. Okay, whether the signal passes through or not. So therein some parameters are involved, as you need to multiply the inputs with some numbers. Okay. So when you have many of them, you have many such numbers. These are like the weights and biases of the linear regression that you have. So when you have many inputs like this, many neurons, each one will have its own weights and biases. So finally, when you predict a result and then you compute the cost function, based on this, you need to update the individual weights and biases of each neutron. But then the signal has to come back layer by layer in the deep neural network. For that, since input, one input brings an output, and this output becomes the input of the next neuron, you have a chain of function of function of function, so on and so forth. So you need to use the Leibniz chain rule and write down products of derivatives to update the weights and biases of each neuron. And this algorithm is called back propagation sequence, you come back from the output to the individual layers. Okay. So yeah, I don't have time to go deep into that. With that, I finish here, and thank you very much.